In Chapter 13, we're going to be talking about gases. So, posing a question, why study gases? Why bother studying gases? Gas is a state of matter that is very different from solids and liquids in some significant ways. And so in some ways, it helps us to understand how matter interacts, and by studying gases, we're able to understand some things that we don't understand from liquids and solids. Studying gases can help us understand some real-world phenomena, like why water boils at different temperatures, at different elevations, things about atmospheric pressure, the pressure in your bicycle tires, a variety of things like that. And also, it helps us to understand a little bit of how science works, because the experiments that were done that determined the gas laws were done back in like the 1600s and the 1700s, and so they are zero technology. And they're much simpler, and so it's easier to understand the process. A lot of the more modern things are just far too complicated for a beginning chemistry class. So let's talk about the properties of gases. And we mentioned these a little bit before when we studied the three states of matter. Gases uniformly fill their container. This is different than solids and liquids. Solids and liquids will not fill up the container. They will retain their volume. But if you put a gas into a larger container, it expands to fill the container. It's a little bit like homework. It expands to fill the amount of time, right? But you can also compress a gas into a smaller volume. So that's really different from liquids and solids. Gases will mix completely with any other gas. We learned about solubility of solids. And so we know that some ionic solids will dissolve in water and others will not. And it's hard to get solids to mix with each other unless you melt them first. But gases, it doesn't matter what the gases are. They will mix thoroughly. They never settle out into layers, and so that's pretty different as well. Another important thing about gases is they exert pressure on their surroundings. So we're going to study about this pressure. What is pressure? Well, in science we define pressure as a force divided by a unit of area. So force over an area. So if the force is greater over the same area, the pressure is greater. If the area is smaller but the force is the same, then the pressure is greater. So think about, well, let's say, what would work? Let's say my husband's laying on the floor and Emily comes and lays flat on top of him. Now she exerts a force laying on top of him, right? She weighs about 90 pounds or so. And when she's laying flat over him, then the area is quite large. And so does it hurt when a child just lays on top of you? No, you feel their weight, right? You feel pressure. Now what if she gets up and she stands in her bare feet on his stomach, both feet on his stomach? That's more pressure, right? Same amount of force, smaller area. Is that going to hurt? Not really. Might be uncomfortable. Now imagine if she put on high heels and stood on one heel on his stomach. That would be so much force, it could actually puncture the skin. A normal woman, 100, 120 pounds, in high-heeled shoes, can punch holes in linoleum because the heel is only like a 1/4 inch square. It is such a small area that her weight exerts a tremendous amount of force. So pressure is a balance between force and area, just like density was a balance between mass and volume. The units of pressure, SI units, are not real useful in chemistry here. These are better for physics. A Newton per meter squared, fabulous, has a special name, the Pascal. Well, we need to know that a Pascal is a unit of pressure, and that's about it. One we use a lot more in chemistry is an atmosphere, or a standard atmosphere. It's abbreviated ATM, which always makes me think of automatic teller machines, but no relationship. An atmosphere is equal to 101,325 pascals. So the atmosphere is a much larger unit. What is an atmosphere? An atmosphere is the pressure exerted by the atmosphere at sea level. Not exactly a real clever name, but it's descriptive. And then there are two other units, millimeters of mercury, which seems like a strange pressure unit, doesn't it? Millimeter is a unit of what? Length. And mercury is an element. It's a liquid element. It's a metal. It's a pretty neat substance, although it's toxic. So a length of a liquid metal as a pressure unit. We'll see why that is in a minute. They also gave that same unit a special name, torr. So torr and millimeters of mercury are just two different names for the same sized unit. But an atmosphere is equal to 760 millimeters of mercury. So where does that millimeters of mercury come from? Well, it comes from the original barometer. A guy named Torricelli made this. A dish of mercury and a glass tube of mercury, completely filled this tube of mercury and then inverted it into the dish. If you do this with a cup of water in your bathroom sink, what happens? Does all the water run out of the cup? No. None of the water comes out of the cup. It's kind of cool. Look at that. The water's defying gravity, right? Well, mercury is a lot more dense than water is, and so some of it will come out, but it will be consistent in the height. It's 760 millimeters of mercury, which is about this long. So it's a pretty long column of mercury. Why doesn't the liquid come out? Have you ever wondered about that? How does it stay up? Because there's a force of gravity, right? Gravity's pulling down, but the atmosphere is pushing down on this liquid out here and is pushing back. And so you get a balance between gravity pulling down and the atmosphere trying to push this liquid back up. Up here, you have an empty space, a vacuum. If this is open, of course, the liquid will come out. But if this is closed, only a little bit of the mercury will come out. What Torricelli found was that the height of this column of mercury was always 760 millimeters of mercury at sea level. But if he carried this up the side of the mountain, as he went higher and higher in elevation, the column of mercury got lower and lower. And then if he carried it back down the mountain, it went up again. And so this was a really important discovery, the discovery of atmospheric pressure. The pressure of the atmosphere pushes down. When you take it to a higher elevation, the atmospheric pressure is less, and so it supports a shorter column. So we can measure pressure as a length of mercury. So that's where that unit comes from. So you should know what a barometer is. A barometer is used to measure atmospheric pressure. Now, of course, we rarely use mercury barometers. We have electronic barometers and all kinds of other things like that. In the lab, on the wall, in each corner, we have a little electronic thing hanging on the wall, and it's got a thermometer and a barometer in it. And so you can go and you can look, and it'll tell you what the atmospheric pressure is, and it's not necessarily the same if you go from corner to corner of the room. It's a little bit different sometimes. So a barometer measures atmospheric pressure. A manometer, you might think, oh, that measures men? The manometer. No, it measures pressure also, but it measures pressure in a container. It's the same idea, though, as the mercury barometer. Here we have an enclosed container with a gas sample in it and it's connected by this tube that's open to the atmosphere up here, but in the tube is some mercury. And so the atmospheric pressure is pushing down on this side of the mercury, and the pressure from the gas here is pushing down on that side. If both of these pressures were equal, then the column of mercury would be equal on each side. The fact that it's higher over here tells us that the atmospheric pressure is greater because it's pushing down more than the gas pressure is pushing down. So we can tell the difference between the pressure inside this container and outside by measuring the difference in the heights of the column of mercury. So this was before electricity was discovered or understood. This was before they knew what an atom was or an electron. But they had devised this method of measuring pressure. If the pressure inside the container is larger than the pressure outside, then this arm of the tube, the mercury will get pushed down, and this side gets pushed up. But again, we can measure the difference in pressure between them. What does the H stand for?
On the bottom, negative H and positive H.
Height. The H down here stands for height. So this is the height, the difference in height. So here the gas pressure equals the atmospheric pressure minus H, because the atmospheric pressure is greater. So we can measure the atmospheric pressure with a mercury barometer. And then to find this pressure, we subtract this. Here, where the atmospheric pressure is less, we're going to take the atmospheric pressure and add H to find the pressure inside. Any other questions? We're not actually going to use a mercury manometer because mercury is toxic and we don't like to let you play with toxic stuff. But we will, when we do, we're going to do a generating hydrogen lab, we will need to understand that if we want the pressure of the gas inside our container to be the same as the pressure outside, then the levels of the liquid have to be the same. In a couple weeks, we're going to generate hydrogen gas, and I'm getting ahead of myself, but what the heck, right? So we're going to generate hydrogen gas, and it's going to be, so there's a water level here, and if the water level inside, here's our hydrogen in there, and this is water. If the water level inside is higher than the water level outside, that means the pressure of the gas in here is less than the pressure outside. If the level inside is lower, that means the gas here is pushing down on the water stronger than the atmosphere is pushing down outside. And so the pressure inside is greater than the pressure outside. We have no way of measuring the pressure inside that tube. But what we can do is we can adjust the height of the tube by moving it up and down. Until the level inside is the same as the level outside. Then we go look at the wall barometer, which measures the atmospheric pressure, and when these levels are the same, the pressure is the same. And so we can measure the pressure inside because we know it's the same as the pressure outside. So we'll be doing that in 2 weeks. This is a cool experiment. One of these semesters I'm going to get it together to do this in lab. So here's a metal can with a screw-on lid. Here the lid is off, and they're heating it with a Bunsen burner, getting the air inside this can really hot. Then when you put the lid on, there's the black lid, screw the lid on while the gas is still hot, turn the burner off. As the gas cools, the can crunches in. It's really cool to see, kind of loud too. Why does it do that? has to do with the pressure. The pressure went down. And we'll find out later that the pressure of a gas is related to its temperature. Okay, so I introduced some pressure units. We need to be able to convert one pressure unit to another. So we've learned how to convert units. We're just going to use it with some different units now. So here's an example. The pressure of a gas is measured as 2.5 atmospheres. Represent this in torr and in pascals. And you do not need to memorize these relationships, but if you go to the table, it'll be set up something like this. An atmosphere equals 760 millimeters of mercury, which equals 760 torr. It equals 101,325 pascals, which equals 1.01 times 10 to the third kilopascals. I guess there was room there. Kilopascals. So that's something like the pressure units will be presented to you. The way these are presented is a little different from most of the unit conversions that we look at, in that all of these are equal to 1 atmosphere. Oh, I just remembered a couple more that'll probably show up on there. 1 atmosphere equals 14.7 psi. You know what psi stands for? Close. Pounds per square inch. Pound is a unit of force. Square inch is a unit of area. So it's a force divided by an area. That's one we're more familiar with. If you fill up your bike tire, it's going to tell you how many psi, what pressure to fill it to. And another one is inches of mercury, and that's what the meteorologists use because they're stuck on English units like most of the country. So they might, like yesterday, we were doing an experiment where we had to use the barometric pressure or atmospheric pressure, and it was 30.13 inches of mercury. And then we had to convert that to atmospheres. So here's the table. The nice thing about how this table is put together is that all of these are equal. And so you never have to do multi-step conversions for pressure. You can always just do one. Because if you need to relate millimeters of mercury to kilopascals, these are equal because they both equal 1 atmosphere. So that's a really nice feature of pressure conversions. So here we've got 2.5 atmospheres. And we need to convert that to torr. It says represent this pressure in torr and pascals. So torr, we're going to multiply by torr and divide by atmospheres. Dimensional analysis tells us how to do that, just to make the units come out right. Then we find the relationship. So we look at our pressure units and we see 1 atmosphere equals 760 torr. So 760 torr per 1 atmosphere. Can't dig my phone out. 2.5 times 760. So 1900 torr. So let's convert that to pascals. We could go back to the atmospheres and convert that, but I think it'd be more fun to do torr to pascals. So 1900 torr, if we want pascals, we're just going to multiply by pascals and divide by torr. And we go looking at our pressure units, and we see 101,325 pascals and 760 torr. We can just pull those numbers out because this number of pascals is equal to 1 atmosphere, and 760 torr is equal to 1 atmosphere. Therefore, they have to be equal to each other. All of the terms in this little table here are equal to each other. So from pascals, we have 101,325, and for torr, we have 760. So we'll take our 1900 times 101,325 divided by 760, and we get a really big number. 253,312.5. That's kind of a ridiculous number of significant figures, isn't it? Our original number had 2. 1900 wasn't the best way to represent that, but it does have 2 sig figs. So here we're going to keep the 2 and the 5. So it's going to be 2.5. But we can't round that off to 25, so we're going to put this in scientific notation. Here's the decimal: 1, 2, 3, 4, 5. 2.5 times 10 to the 5th. That's a better way to give the answer. Any questions? The vapor pressure over a beaker of hot water is measured as 656 torr. What is the pressure in atmospheres? So the vapor pressure, the hot water business, that's just a little backstory. We just need to convert torr to atmospheres. 656 torr. I'm going to multiply this by a conversion factor. What do I want? What unit on the top? Atmospheres. And what unit on the bottom? Torr. For the numbers, I go to the table. And what number is in front of atmospheres? 1. Remember what was in front of torr? 760. We're going to use that 760 a lot. 1 atmosphere is 760 torr, or 760 millimeters of mercury. So that's one that's worth memorizing. You might memorize it in spite of yourself, just by using it too much. So 656 times 1 divided by 760. Calculator says 863,15789. Atmospheres. Well, that should have 3 sig figs, right? 656. This 760 is an exact number. Okay, the millimeters of mercury in the atmosphere are defined so that exactly 1 atmosphere is exactly 760 millimeters of mercury. So this is not going to limit the number of sig figs in our answer, so this should have 3. So we pick out the answer is B. Any questions? That's an excellent exam question right there.